Hi, I'm Henry Burns, a student at Georgia Tech, and today I'll be talking about forensic signatures from laser isotope separation. To start, atomic vapor laser isotope separation, or AVLIS as it's commonly known, is a method of uranium enrichment that relies on tuning lasers precisely to selectively ionize uranium-235 in a vapor cloud. Once ionized, the atoms can be collected by a negatively charged collection plate. AVLIS is very energy efficient, which makes it an attractive enrichment option, but the same energy efficiency could potentially make it harder to detect, and so that poses a proliferation risk. For this reason, we're interested in developing both forensic signatures that can potentially be used to detect a clandestine AVLIS facility, and inspection tools that can help inspectors analyze a legal, commercially operating AVLIS facility. This is in line with the NNSA mission, in which treaty enforcement is very important. And so these tools can help ensure that treaties surrounding uranium enrichment are indeed enforced. For our technical approach, we model the product stream as a mix of uranium-235 and natural uranium. This is due to the selective ionization of 235, and then factors such as charge exchange and the geometry of the AVLIS device, delivering a certain portion of the feed unmodified in assay to the product stream. To the product stream. And this is known as the non-selective pickup, and it's one of the principal important operating parameters of an AVLIS device. The other one of note is the stripping efficiency, designated eta, which is a measure of the proportion of uranium-235 in the feed that is ionized and then collected. And for the following work, we also assume a feed of natural uranium. So as a result, we find a few important things. One is that the stripping efficiency can be determined entirely by looking at the tails assay, and that the non-selective pickup can then be determined by looking at the stripping efficiency and the product stream. And so in this way, this provides a good tool for inspectors because it turns out that we can determine key operating parameters purely by looking at the product, feed, and tail stream, and don't have to look at the design of the machine itself. It also turns out that we can determine the amount of secondary isotopes, like uranium-234, present in the feed only by looking at the product. And this is very useful because different uranium mines have slightly different 234 to 238 ratios. And so if by looking at the product we can determine the original feed, we can potentially determine the source of that feed uranium. We can also apply a thorium-230 chronometer, in which we look at the ratio of thorium-230 to uranium-234 due to the buildup of thorium over time from the decay of uranium-234. And this lets us know when the uranium was last enriched. So as an expected impact, the ability to determine machine parameters purely through analysis of product and tails will be of use to facilities inspectors, and giving the product assay of uranium-234 in terms of the feed assays should allow for accurate determination of the original feed assays. The MPV impact of this work. So MPV has impacted the development of this work very directly in that it provided the opportunity to collaborate with a researcher at Lawrence Livermore over the summer, and a lot of this work is due in large part to that. And moving forward, MTV has also provided the opportunity to collaborate with more researchers at Livermore, in which I will use the knowledge base gained from analyzing AVLIS to implement a photoionization model that we expect to help improve a RIMS detection system. As next steps, we will pair this work with known isotopic ratios from different mines to serve as a reference, and we will investigate possible ways this analysis could be frustrated by facilities seeking to divert enriched uranium and design appropriate countermeasures. Thank you.